Hi guys, so now we are going to continue our lecture for the chapter 3 gas turbine cycles. So gas turbine cycle, also you can call it as a Brayton cycle. So from the last topic, we only learned about the ideal cycle of the Brayton cycle. So now how we want to improve the Brayton cycle. Okay, one of the improvement is we call it as regeneration, the Brayton cycle with regeneration. So this is the same thing like vapor cycle. Remember, if we say that this is a regeneration, so there is a preheat process occur in the cycle. Okay, so let's look at here. In gas turbine engine, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of the air leaving the compressor. So here it said that the temperature here coming out from the turbine is higher than the working fluid that coming out from the compressor. Okay, so if the wasted heat from the turbine here, we can use it to preheat the working fluid that coming out from the compressor. When we preheat the air here, so it will help combust the fuel here. Okay, so it will increase the efficiency. Therefore, the high pressure air leaving the compressor can be heated by the hot exhaust gas in a counterflow heat exchanger. So this is the exchanger, this is the heat exchanger. Okay, so the hot exhaust gas here, we can use it to preheat the air here, okay, to help the combustion become more efficient. The thermal efficiency of the Brayton cycle increases as a result of regeneration, since less fuel is used for the same work output. So if the air that we use for combustion is in a hot condition, so it can reduce the usage of fuel. Okay, so here the TS diagram, how it looks like when the Brayton cycle is implementing the regeneration. Okay, so if you look at here, this is the portion of regeneration. Without regeneration, this portion is exists, which means that the state 4 is at this location. Okay, so state 5 is a state 2. When there is a regeneration, so the TS diagram here is increased. The area of the TS diagram is increased. So when the area of the TS diagram increase, or the area of the work net is increased, so in the same time the thermal efficiency is also increased. So here how we formulate the regeneration in the Brayton cycle. So if you look at here, air normally leave the regenerator at lower temperature T5. So T5 here is the minimum temperature before regeneration. So after we regenerate using the temperature at T4, so the maximum regeneration temperature will be at T5 prime. Okay, so this is the maximum temperature before it's enter the boiler. After the boiler at the state 3, it's further increase the temperature. Okay, so this we call the ideal cases. In ideal cases, the air exit the regenerator at the inlet temperature of the exhaust gas T4. Okay, which means that the temperature here is same as the temperature of the exhaust at T4. Okay, so this is the ideal condition. So normally in actual condition, it must be less than ideal. Okay, so if you look at here, Q regeneration actual is equal to H5 minus H2. H5 somewhere here, H5 minus H2, and for the Q generation maximum is H5 prime, this is maximum, minus H2. phi prime also same value with the H4. Okay, so H4 minus H2. So from here we can calculate the effectiveness of regenerator. So how much the actual is approaching the maximum value of regeneration. So we just do like this, H5 minus H2 over H4 minus H2. Okay, or for the under cold air standard assumption, so we can replace enthalpy value with the temperature, T5 minus T2 over T4 minus T2. Okay, so this is the efficiency of regeneration under cold air standard assumption. Okay, so since we know that thermal efficiency for the Brayton cycle is depend on the threshold of the minimum to maximum temperature as well as the pressure ratio, so regeneration is most effective at lower pressure ratio and low minimum to maximum temperature ratio. So if you look at this diagram here, so this is the pressure ratio and this is the efficiency of the Brayton cycle. So this is without regeneration. Without regeneration, as the pressure ratio increase, the thermal efficiency is also increased. But different with regeneration, it is most effectively increase the efficiency of Brayton cycle at the lower pressure ratio. Here, the maximum is 15, and then at lower temperature ratio. Yes, the temperature ratio is here. This is the lowest one. Okay. Next improvement in the Brayton cycle is also you can use the reheating and intercooling process. Okay, so the concept is to minimize work input to the compressor. So we want to minimize work input and then maximize work output at turbine and maximize the work output at turbine. By minimizing the work input and maximizing the work output, you will get the increasing in work net. Okay, if as the work net is increased, the thermal efficiency is also increased. That's the concept. So how we do the minimizing work input and maximizing the work output? So you might want to put the intercooling process here. So the intercooling process here, as you can see here, carrying out compression process in stage and cooling the gas in between. Okay, so by cooling the gas in between, your work to compress the gas will be much easier. If the hot gas, if you want to compress the hot gas, more work is needed. So if it is cool, so the compression process will be much easier. Okay, so and then we want to maximize the work output, so we put reheater here, so expanding gas in stage and reheating it in between. So the work output will be increased because we reheat the gas and then to expand the turbine, to expanding in the turbine. Okay, if there is only one turbine without reheating, so there more heat is wasted to the environment. So if we reheat the gas and go to the turbine too, so the total work will be increased. Okay, so the regeneration process will remain here. Okay, so the TS diagram will become like this. This is the TS diagram. So this is state 1. The state 1, after you compress, it will increase the temperature, and then you put intercooler between two compressor. The gas will be cooling down and then compress again. And then after that, in the combustion process here until at the state 6, and then after expanding in the first turbine, so there is a reheater here between these two turbine, and we reheat again the gas. After that, it sink in the exhaust. Okay, so here from state 9, it will have the regeneration process, which is recovery the heat, the waste heat from the exhaust. Okay. So as I said earlier, multi-stage compression with intercooling, the work required to compress a gas within two specified pressure can be decreased by carrying out the compression process in stages and cooling the gas in between. This keeps the specific volume as low as possible. Okay, and then multi-stage expansion with reheating keeps the specific volume of the working fluid as high as possible during an expansion process, thus maximizing work output. Now let's look at the PV diagram here. Okay, this is the comparison of work input to a single stage compressor, which is 1AC, and a two-stage compressor with intercooling, which is 1A, B, and D. So this is the ideal line, which is the isothermal line. Isothermal, which means there is no heat is wasted to the environment. So this is the ideal condition. So when you implementing the intercooling process, so it will pushing the ideal condition, okay, from A to B and D. Okay, so that's the improvement of the intercooling process. Okay, and then as the number of compression and expansion stage increase, the gas turbine cycle with intercooling, reheating, and regeneration approach the addition cycle. So if we increase the number of reheating process here and the intercooling process here, so the TS diagram of the Brayton cycle will approaching the addition cycles. Keep in mind that intercooling and reheating without the regeneration process will decrease the thermal efficiency. Okay, this is because intercooling and reheating always intercooling decrease the average temperature at which heat is added. Okay, so and reheating increase the average temperature at which heat is rejected. Okay, which means that intercooling it decrease the temperature. Okay, decrease the temperature, so more heat is required to increase the temperature. So this is where there is no preheat process, and then also reheat increase the heat rejected to the environment. Okay, so that's why both intercooling and reheating will need the regeneration process in between. Okay, because the regeneration will recover the heat rejected from the reheating process, and then they preheat the cooling air in the intercooling region. Okay, now let's look at some problem here. Okay, if let's say an ideal gas turbine cycles with two stages of compression, which means there is two compressor and two stage of expansion, there is two turbine, has an overall pressure of 8. Okay, air enters each stage of the compressor at 300 Kelvin and each stage of the turbine at 1300 Kelvin, which means at the compressor state there is two compressor here, and then two turbine here, two stage of turbine. So each stage has a pressure ratio of 8, and this one is also 8, and then the temperature at the compressor inlet is 300 Kelvin, and then at the turbine is 300 Kelvin. Okay, when the question said that there is a 2 stage of compressor and 2 stage of turbine, so it is understand that there is a intercooler in between and a reheat process in between. Okay, so your TS diagram should be like this. Okay, so this is state 1, 2, and then this is a intercooler 3, 4, this is reheater. Let's say this is 6, and then this one is 7, 8, 9. Okay, TS diagram. So your graph is like this. This is state 1, compress, intercool, reduce the temperature. State 2, 3, after intercooling, compress again. Number 4, and then enter the boiler, increase temperature, and then go to state 6, and then go to turbine, expansion, expand the gas, so reduce the temperature, and then reheat again, increase the temperature. So this is 6, 7, this one 8, go and then reduce to the exhaust 9 and complete 1 cycle. Okay, if there is a regeneration process, the state will go to the state 5. State 5 is over here if there is a regeneration. Okay, now let's imagine if there is no regeneration yet, so how much the thermal efficiency. Okay, this is for question A, so we do this first without the regeneration first. Okay, so if you look at this TS diagram here, okay, the temperature for this is the same. Stage 1 and 3 is same. Stage 6 and 8 is also same. Okay, so which means we can simplify our analysis like this. Pressure T1 is equal to T3. Okay, and then T2 and T4, T2 is equal to T4. Okay, what else? This one, T6 is equal to T8, and T7 is equal to T9. This one, T7 is equal to T9. Which means that this is also equivalence to H1 is equal to H3, H2 is equal to H4, H6 is equal to H8, H7 is equal to H9. This means that once you get the H1 and H2, you don't need to find the H3 and H4 because it is equal, same like H6 and H7. Once you get the H6 and H7, you don't need to find the H8 and H9. Okay, and then one more simplification is P2 pressure ratio for this stage. P2 per this stage, P2 per P1 is equal to this pressure ratio is equal to this pressure ratio, which means P4 per P3. So this is a 2-stage compression process, and then this is 2-stage turbine or expansion process. So these two stage also the pressure ratio is equivalent. P6 per P6 over P7 is equal to P8 over P9. Okay, so these two is equal to P is equal to 8. These two stage is equal to pressure ratio Rp is equal to 8. So to get each of the pressure ratio you need to square root. Okay, so which means that P2 per P1 is equal to P4 per P3 is equal to square root of 8 is equal to 2.83. Okay, if there is a two compressor, so when you multiply, so it's equal to 8. Okay, so same for this one, P6 over P7 is equal to P8 over P9 is equal to square root of 8. It's equal to 2.83. Sorry. Okay. Okay, so from all the information here, then we can calculate the thermal efficiency. So as usual, let's find the enthalpy at state 1 first, okay, which is H1. So using the information of T1 is equal to 300 Kelvin, because here is 300 Kelvin, and then the maximum is 1300 Kelvin. Okay, this one is 300 Kelvin, so refer to the table A17. Okay, so you will get H1 is equal to 300 kilojoule per kilogram. So also get the relative pressure PR1 equal to 1.386. So from the relative pressure of state 1, so you can get the relative pressure at state 2 using this equation. PR2 is equal to pressure ratio multiplied with PR1. So you will get square root of 8, 1.386. So this one is equal to 392. So use this value to get the value of T2 and H2. So if you refer at the table A17, you will get the T2 is 403.3 Kelvin, 404.31 kilojoule per Kelvin. Okay, so how about the state 3 and 4? You don't need to find the value of enthalpy, because if you look at here, H1 is equal to H3, so which means that this value is also represent for H3. H2 is equal to H4, so this value is also for H4. Okay, so now let's find the enthalpy at state 6 here, which is at the maximum temperature. So T6 is equal to 1300 Kelvin. So refer at the table A17 as usual, so you will get H6 is equal to 1395.797 kilojoule per kilogram. Okay, so get the relative pressure for PR6 is equal to 0.9. Okay, from this one you can calculate the PR7, the same process that you do this one here. Okay, so P7 per P6 PR6 is equal to 1 over square root of 8 to 30.9. Okay, this one you will get 117.0. Okay, okay, now get the, using this relative pressure value, get the T7 and H7. So you will get 1006.4 Kelvin, 1053 kilojoule per Kelvin. Okay, so this one is the you already complete the calculation for state 6 and 7. So how about 8 and 9? 8 and 9 you don't need to do the same process, because it is based on this formula. So H6 is equal to H8, H7 is equal to H9. Okay, now we already get all the value of the enthalpy for each of the states, so we can calculate the thermal efficiency. Okay, thermal efficiency as usual is equal to work net or work compressor in minus work turbine out minus work compressor in divided by Q input. Okay, so where is your Q input? Q input is here between the state for 6 and 7 and 8. This is your Q input. Okay, so what about your work compressor in? Your work compressor in is between state 1 and 2, 3 and 4, because there is a 2 stage of compressor, right? So this is work input, and then your turbine out is here between 6, 7 and 8, 9. So this is your work turbine out. So if we can write down here the formula, work compressor in is equal to H2 minus H1 plus H4 minus H3, because this value is same like this value, so we just assume it to multiply assume it there is a two things like this here. Okay, so this 2 H2 minus H1. Okay, so work turbine out, same thing, is equal to H6 minus H7, H6 minus H7 plus H8 minus H9, because these two things is the same formula, same value, so we assume there is two things like this. Okay, 2 H6 minus H7. Okay, so your work net is equal to 2 H2 minus 2 H6 H7 minus 2 H6 H2 minus H1. Okay, so what is your H6, H7, H2 and H1? You already calculate here just now. Okay, just substitute into the equation to 1395.97 minus 102 minus 2. Okay, so your work net you will get 477 0.04 kilojoule per kilogram. Okay, your Q in is equal to this is your Q in H4 H6 minus H4 and then H8 minus H7. Okay, so Q in is equal to H6 minus H4 plus H8 minus H7. Okay. So this one is equal to, so you can take this value H6 minus H7, 1395.97 minus 1053.33, and then plus your H8 is equal to H6. Okay, so the value of H8 is also this value, 1395.97 minus H7 is 1053.33. This one is equal to 1334.30. Okay. So your efficiency, you will get 1334.30 is equal to 0.358 or 35.8%. So this is your efficiency when the Brayton cycle is implementing intercooling and reheating, but without the regeneration. So you will get the thermal efficiency is much lower than the one without the intercooling and reheating or ideal Brayton cycle. So intercooling and reheating without the regeneration process is hurting the thermal efficiency. So if you don't want the thermal efficiency to be dropped, so you need to accompany the reheating and intercooling process with the regeneration process. So what if we implement the regeneration process? So here we go. If there is a regeneration process, so there is a state 5 here. So we regenerate using the temperature from the exhaust at the state 9. So the regeneration will go to the state 5 here. Okay, so your Q in will become this is your new Q in. So your Q in is equal to H6 minus H5, okay, plus H8 minus H7. Okay, so what is the value of your H5, sorry? So your value H5 is equal to, because this is the same at the same temperature condition, so H5 is equal to H5, H7 equal to H9. Okay, so you can take the value of H7. What is the value of H7? H7 is equal to 1053.33. Okay, so substitute into the equation, 1395.97 minus 1053.33 plus 1395.97 minus 1053.33. So you will get the value for Q in is 685.28 kilojoule per kilogram. Alright, so this value Q input is much lower than the value of Q input without the regeneration. Okay, So as Q in is reduced, so the thermal efficiency is supposed to be increased. So this is the new thermal efficiency is equal to 47704. This one substitute in here, 685.28 kilojoule per kilogram. So this is equal to 0.9696 or 69.6%. Okay, so this is much higher than the thermal efficiency without the regeneration. So intercooling and reheating should be accompanied with the regeneration. Okay, so from then we can improve the thermal efficiency of the ideal Brayton cycle. Ideal Brayton cycle without the improvement from the previous problem, from the same problem, will produce the efficiency equal to 42.6%. Okay, so without regeneration is lower than this one, and with regeneration is higher than this one. Okay, this one. Okay, so okay, that's it. Thank you.